Hello and welcome to the lecture on 6.3. Today we're going to talk about trigonometric functions of angles. An angle is in standard position if the initial side is on top of the positive x-axis and the vertex is at the origin. Let me go ahead and show you exactly what I mean, in case you've forgotten. Suppose that we have this angle here. Then we can create a triangle, giving us a y value here, an x value here, and this point would be pxy. And then r is here, would be the radius of the unit circle if we drew the circle here. Now this angle theta is in standard position because the vertex of the angle is at the origin, and the initial side of this angle right here is on top of the positive x-axis. So as we've seen before, we have our trig ratios. And we're going to redefine these in a second. So sine of theta would be opposite over hypotenuse, which would be y over r. Cosine of theta is adjacent over hypotenuse, which would be x over r. And tangent of theta is opposite over adjacent, which is y divided by x. Let's redefine our trig functions. Let theta be an angle in standard position, and let pxy be a point on the terminal side of the angle. If r is equal to the square root of x squared plus y squared is the distance from the origin to the point pxy, then sine of theta is equal to y over r. Cosine of theta is x over r. Tangent theta is y over x. And then we have the reciprocal functions. Cosecant theta is r divided by y. Secant theta is r divided by x. And cotangent theta is x divided by y. Now for secant and tangent theta, x cannot equal 0. And for cotangent and cosecant, y cannot be 0. Otherwise, we would have an undefined trig function expressing what the domain is. Now, let me explain this a little bit. Now, it might be worded a little bit unusually. So suppose that we have our xy plane here. If we extend out our terminal side, of course, our initial side is on the positive x-axis. As we said, the angle is in standard position. A requirement to be in standard position means that the initial side of the angle is on top of the positive x-axis. So now, if we have some point pxy, it doesn't matter if this point is on the unit circle or not. If this point pxy is anywhere on this terminal side of the angle, then these ratios will hold, assuming again that r is equal to the square root of x squared plus y squared. So the distance from the center to the point P, meaning that this distance is r. This distance is, of course, y. This distance is x. So if we push this point out farther on the terminal side of the angle, we would still have a point pxy, but our x would be a little bit farther, our y would be a little bit taller, and our r would be a little bit longer. The lengths of the sides don't matter when it comes to the trig ratios, because the ratios will always reduce to the same value. I'll show you what I mean in a second here. Nope. Suppose we have our xy plane, we have our terminal side of a point. Say that we have a point here, pxy. This is a terminal point. Suppose we also have another terminal point, px prime y. This. So, if we draw a triangle here and we draw a triangle here, these two triangles are similar triangles. Now, what I was trying to get at a second ago with it doesn't matter where this point is on the terminal side. Right, so this would be y, this would be x, and we would have our r here. And we also have an r prime here. This would be y prime, and this distance would be x prime. So what I'm trying to say here is that because these two triangles are similar, the ratio of y prime to r prime is the same as the ratio of y to r. What that means is that sine of theta is exactly one number. Now, it will equal, for the small triangle, y divided by r. But for the big triangle, sine of theta is equal to y prime divided by r prime. Since sine is a well-defined function, it has exactly one output here, or some angle theta. Now, this angle theta didn't change. It's the same angle for this big triangle and the small triangle. So sine theta here and sine theta here are exactly the same number. So what that means then is that y over r is equal to y prime divided by r prime. We can say the exact same thing for cosine. Cosine of the same angle theta, because this angle doesn't change, we have that cosine of theta is equal to x over r, and the same angle, cosine of theta, is equal to x prime over r prime. And again, because this angle doesn't change, and cosine is well defined, these two values are exactly the same, which means that x over r is exactly the same as x prime over r prime. And of course, we can do tangent as well. Tangent of theta is equal to y divided by x for the small triangle, and tangent of theta is equal to y prime divided by x prime for the larger triangle. Again, the angle didn't change, and tangent's well defined, which means then that y divided by x is equal to y prime divided by x prime. This is what I meant when I said that as long as the point is on the terminal side of the angle, it doesn't matter how far away from the origin it is. It could be here or it could be here, it'll still give the exact same ratio. It just reduces to the same number. Let me show you what I mean here. Do an example here. So in this small triangle, we can say that this length is 5, this length is 3, and this length is 4. This distance is 8, exactly twice the distance of 4. Now, that means then that 3 is also going to be exactly twice the distance. So we have 6 here. This would be 10 to get to this point. So if we looked at the angle theta, and we look for sine, cosine, and tangent of this angle theta, we're going to get the same ratio. So sine theta for the small triangle would be 3 divided by 5, and sine theta for the big triangle would be 6 divided by 10. Now 6 divided by 10 reduces to 3 divided by 5. Just divide top and bottom by 2. Similarly, cosine of theta would be 4 divided by 5. But for the big triangle, cosine of theta would be 8 divided by 10. And again, 8 divided by 10, if you divide both of these by 2, you get 4 divided by 5. And of course, tangent will also yield a similar result. We would have 3 divided by 4, or 6 divided by 8. This should make sense, again, because the angle is not changing. So this ratio should be the same. It doesn't actually change. It's exactly one number, no matter which numbers we choose to use. I will note that we are also using positive and negative values of y and x from the unit circle. So this would also hold for positive and negative values of x. I will note that this also works for positive and negative values. When we look at the unit circle, remember that going around the unit circle, we have larger and larger angles. So we can do something angle over here, say 2 pi over 3. And we would have a negative x value. It still does not matter where on the terminal side of this angle the point is, as long as it's on the terminal side, then we would get the exact same result. So let's say that this angle is 2 pi over 3. then we have cosine of 2 pi over 3 is exactly negative 1/2. Let's say that this is exactly the 1/2. So if we have here 1, we'd have negative 1/2 here, and this would be root 3 over 2. Let's again assume that this is twice the distance, so this would be a negative 1. This distance would be root 3, and this distance would be 2. Cosine of 2 pi over 3. For the bigger triangle, if we look at the triangle, we know that we have a negative value here, so we'd have a negative 1 divided by 2. We get the exact same ratio. It doesn't matter if we have positive or negative signs as well. I'm going to remind you now which functions are positive and negative in which quadrants. We have our positive function and our negative. So in quadrant 1, the positive functions are all of them, and we have no negative functions. 2, the positive functions are sine, secant, and the negative functions are cosine, secant, tangent, cotangent. Quadrant 3, we have that the positive functions are tangent and cotangent. And then we have sine, cosecant, cosine, and secant are all negative in quadrant 3. In quadrant 4, we have cosine is positive and secant is positive, which means then that sine, cosecant, tangent, and cotangent are all negative. If you look at the breakdown on the quadrants, quadrant 1, 2, 3, and 4, we can see the signs of our x and y values and really easily derive each of these. So in quadrant 1, x and y are both positive, which means then that all of them are going to be positive because sine and cosine are both positive, which means tangent is also positive. I will note that the hypotenuse of these triangles, when we draw the terminal side of our angle, is always positive. We would have a negative x value, positive y value. Since the y value is positive, sine is positive. X value is negative, cosine is negative. Quadrant 3, both x and y are negative. So when we do y divided by x, in the case of tangent, we would get a positive function. And then in quadrant 4, x is positive, but y is negative, so cosine is positive because it refers to the x. Let's go ahead and do an example really quickly here. Find cosine of 210 degrees and tangent of 420 degrees. On our unit circle, we look for the angle 210 degrees, and that's actually right here. 210 degrees. It's just past, it's 30 degrees past 180. 180 degrees is the same as pi radians. And if our point pxy is here, we need to figure out what cosine is, because that's what we're looking for. So cosine is going to be the x coordinate. And this is negative root 3 over 2, negative 1/2 on the unit circle. So cosine of 210 degrees is negative root 3 over 2. By now you should have the unit circle memorized. So I'm not going to go back to it very often. Now for tangent of 420 degrees, this one might be a little bit more tricky. Mainly because 420 degrees is beyond 360. So it's a full circle and then a little bit more. Specifically, it's a full circle and then 60 degrees more. So if our point here is pxy, this would be 1/2 root 3 over 2. If you look at the unit circle, and our angle looks like this. It's 420 degrees. So tangent of 420 would be root 3 over 2 divided by 1/2. Root 3 divided by 2 divided by 1/2. And we flip and multiply the denominator. The 2's will cancel, and we're left with just square root 3. So this would be the answer for tangent of 420. The next topic I want to talk about is reference angle. I want to make a note before I define what a reference angle is. The reference angle and the reference number are identical concepts. The reference number moves along the unit circle, so that is radian measure. The reference angle can be in any angle measure. Definition. Let theta be an angle in standard position. The reference angle theta bar associated with angle theta is the acute angle formed from the terminal side of angle theta and the x-axis. So what this looks like is exactly the same as the reference number. Each quadrant will have a different way of finding the reference angle. So if we're in quadrant 1, that means that our terminal side is in quadrant 1. Then we have this angle here, theta. Now, an acute angle, remember, is less than 90 degrees. So the angle that's formed from the terminal side of angle theta and the x-axis would be this angle here. So in quadrant 1, theta bar is equal to theta. Now, if we're in quadrant 2, it's a little bit different. So suppose that our angle is in quadrant 2, meaning that theta is obtuse. It moves from the positive x-axis all the way into quadrant 2 where the terminal side of the angle is. Now in quadrant 2, our reference angle is going to be this angle here. It's an acute angle, an angle less than 90 degrees, formed from the terminal side of angle theta and the x-axis. So we take the terminal side and the x-axis. This is the acute angle. This angle here would be theta bar. Now, if you remember how to find the reference number from last chapter, it was t bar is equal to pi minus t. Now, it's identical here, except we're using thetas. So we would have theta bar is equal to 180 degrees, because we're using degrees right now, minus theta. Again, this angle here is theta bar. We take the angle 180 degrees, and we subtract off the part we don't want. We want to keep theta bar, so we subtract off theta. Or you can think of it a little bit differently. Theta plus theta bar is equal to 180, and then subtract your theta over to solve for theta bar. Now, if we're in quadrant 3, then our angle looks like this. This is theta. Now, our theta bar, again, is the acute angle formed from the x-axis and the terminal side of theta. So this would be theta bar. So, how do we figure out what theta bar is? Well, again, this is 180 degrees, a straight line. This would be 180 degrees. So we would have 180 plus theta bar is equal to theta, because theta passes 180 degrees. So you could think of it as theta bar plus 180 is equal to theta. If you subtract the 180 over, you have theta bar. So we'd have theta minus 180 degrees. Now in quadrant 4, same idea. This is angle theta. Now, theta bar is the acute angle formed from the terminal side of theta and the x-axis. So this is theta bar here. Quadrant 4. Now, an entire circle is 360 degrees. Theta plus theta bar gives us an entire circle in this case. So, theta plus theta bar is equal to 360. And then if we wanted to solve for theta bar, which is what we want to find, we subtract theta over. So we have theta bar is equal to 360 degrees minus theta. So this is how we find theta bar for each quadrant. And again, it's identical to last chapter when we were talking about the reference number. Example, using the reference angle to evaluate trig functions. Let's find tangent of 210 degrees. I'm going to go ahead and plot this angle first, and then we'll show you how to use the reference angle. Now remember, we talked about 210 degrees already. This is 210 degrees. It's 30 degrees past 180. 210 degrees. So we're in quadrant 3. So you need to remember, first of all, that tangent is positive in quadrant 3. And that's from about 5 minutes ago in this lecture. The theta bar that we're looking for is here. This is what we're going to use to evaluate tangent. Theta bar is equal to 210 minus 180. So we get 30 degrees. What we're going to do is we're going to find tangent of 30 degrees. Now, tangent of 30 degrees will always be positive. 30 degrees, like all reference angles, is an acute angle. It's in quadrant 1. So whenever we use a reference angle in order to find a trig value, we're going to get an angle that's in quadrant 1. Now what that means is that we're always going to have a positive sign. We need to amend this to include a sign with our trig evaluation. So tangent of 30 degrees is going to be positive. We need to figure out what tangent of 210 degrees is, and 210 degrees is in quadrant 3. So tangent will be positive in quadrant 3. So I'm going to go ahead and assign the sign positive. Tangent of 30 degrees is exactly 1/2 divided by root 3 over 2. And we carry this sign down, so we have a positive value, flip and multiply, and we get 1 divided by square root 3, or root 3 over 3 if you rationalize the denominator. Go ahead and try one on the accompanying worksheet. Find sine of 300. And tangent of negative 405 degrees. Now keep in mind, this is bigger than 360, so it's more than a full circle. Let's rewrite the trig identities with angles theta instead of t now. Remember that. Remember the reciprocal identities? We have that cosecant of theta is equal to 1 divided by sine. Secant theta is 1 divided by cosine. Cotangent theta is 1 divided by tangent. And then we always include, for some reason, tangent of theta is equal to sine of theta over cosine of theta. And cotangent of theta is equal to cosine of theta divided by sine of theta. The Pythagorean identities, as you might remember, sine squared theta plus cosine squared theta is equal to 1. Tangent squared theta plus 1 is equal to secant squared theta. And 1 plus cotangent squared theta is equal to cosecant squared theta. These are identical to last chapter, except instead of a t, which was a distance around the unit circle, meaning that that t value was in radians, we have angle theta. This is a little bit of a generalization in that theta can be in any angle measure, not just radians. I'm not going to prove these because I proved them last chapter, and I don't feel like it's going to benefit anyone to prove. I want to do another example of something that we did last chapter as well, but I know that this example is a little bit difficult for students, so I'm going to go over another one just like. Express cosine theta in terms of sine theta, where theta is in quadrant 2. So what you want to do, if you can, you can't always do it, but if you can, find a relationship between sine and cosine. And that relationship in this case is the Pythagorean identity. We have sine squared theta plus cosine squared theta is equal to 1. Now, if you're trying to do this with tangent and cosine, or tangent and sine, or cotangent and cosine, or cotangent and sine, then it becomes a little bit more difficult. You would still use the Pythagorean identity, you just wouldn't use the one with tangent or cotangent. You're still going to use this same Pythagorean identity, but you also have to remember that tangent is sine over cosine, and cotangent is cosine over sine. And that's what you'll do in the try one problem in a second. If we're to solve for cosine, as it says in the problem, express cosine in terms of sine, so we want to solve for cosine, we get that cosine squared theta is equal to 1 minus sine squared theta. Now, I want to solve for cosine, not cosine squared. So I'm going to take the square root of both sides, and we get cosine of theta equal to plus or minus the square root of 1 minus sine squared theta. Now, this is not reducible, so do not reduce this. It's a common mistake. Please don't be that student. But notice that we have two different answers. We have positive square root 1 minus sine squared and negative square root 1 minus sine squared. So which one is the actual answer? Well, we go back now and look at theta, and we have to remember what the sign of cosine is in quadrant 2, because theta has a terminal side in quadrant 2. Cosine is negative in quadrant 2, so we're going to use the negative value. So cosine will equal negative square root 1 minus sine squared theta. And we're done. Now I want you to try one on the accompanying worksheet. Write tangent theta in terms of sine theta, where theta is in quadrant 3. What I mean by this is that the terminal side of angle theta is in quadrant 3. You have to be careful with this one. Remember, tangent is equal to sine over cosine. Now, you'd still have a cosine, so you still need to get rid of this cosine. And in that sense, you're going to be writing cosine in terms of sine. Do another example. If cosine of theta is equal to 5 divided by 13, find tangent of theta when theta is in quadrant 4. You have to be careful here. And I'll show you a trick when you draw out your triangle. So a lot of times, we still want to use the unit circle, but we don't need to draw it every single time. Most of the time, what I do is just draw a triangle, but I know that my angle's in quadrant 4. I'm going to draw my triangle in quadrant 4. It's going to look like this. Now to draw the triangle, we use this acute angle here. This is theta bar. It's the reference angle. We know that the x value is 5, and we know the hypotenuse is 13. We can write it like this. Since the angle theta is in quadrant 4, giving us a terminal side here, I can tell that my y value is going to be negative. That's why I draw my triangles upside down in this case. So if I were to draw a triangle, instead of drawing a unit circle, I would draw it like this, where I know my x value is 5, my hypotenuse is 13, and I know my y value is negative because I've indicated it by drawing my triangle upside down. I know that because we're in quadrant 4. How do we find this third side? Triangle. Well, we could just use the Pythagorean theorem. X squared plus y squared is equal to r squared, where r is our hypotenuse length. So in our case, our x is 5. 5 squared plus y squared is equal to 13 squared. Subtract the 25 over, and our y squared is equal to 169 minus 25, which gives us 144. Take the square root, and we'll have y is equal to plus or minus 12. So is it going to be the positive 12 or the negative 12? And this is where drawing your triangle upside down helps, because we can see that the y value is negative. It's indicated. So this is negative 12. Negative 12. We also can tell from quadrant 4 that the y value is going to be negative, so we know we use the negative if you don't want to draw your triangle upside down. So now when I'm looking at this triangle, I'm looking for tangent of theta, which is the opposite over the hypotenuse. Tangent theta is equal to negative 12 divided by 5. And that's it. Try one on the accompanying worksheet. A. If sine of theta is equal to negative 3/5, find tangent of theta if theta is in quadrant 3. B. Use the answer in the previous question to check your answer to part A. Now this might sound a little bit confusing. What I want you to do is use your answer here in this try one problem. Notice that we have tangent in terms of sine. So if I know what sine is, I should be able to figure out what tangent is when theta is in quadrant 3. So use that answer to figure out what tangent of theta is when theta is in quadrant 3 if sine is equal to negative 3/5. The next topic I want to talk about is area of triangles. Definition. The included angle is the angle between two known legs of the triangle. So if we know we have a triangle that looks like this, and we know A and B, then theta is the included angle. If we said that this was angle theta, then theta would not be the included angle. So this is the angle that's included between A and B. All the area of a triangle is A is equal to 1/2 base times height. So what I'm going to do next is draw a picture. Remember this formula from geometry a long time ago. What I'm going to do next is draw a picture. Suppose that we have a triangle that looks like this. So here's our triangle. Now, if I knew what the base was, B, and I knew what the height was, H, then I could find the area of this triangle by just doing area is equal to 1/2 base times height. But suppose that I don't know the base and the height. What if I know two legs of the triangle, A and B, and I know the included angle? We can still find the area of the triangle very easily because we can find the height of this triangle just by using sine function. Sine of theta is h divided by a. So that would be sine of theta is equal to h divided by a. And if we solve for h, then we get that h is equal to a times sine theta. So now I know what the height is of this triangle, and I can use this formula, this area formula, to find the area of the triangle. So now area will equal 1/2 base times height, where our base is b, this entire leg of the triangle that we already know. And I know what h is. H is a sine theta. So area is going to be 1/2 times a times b times sine theta. So what I'm saying here is that if I know two legs of a triangle and I know the included angle, I can find the area of this triangle just by using this formula here. Suppose instead we had an obtuse triangle, meaning that it has an angle. Suppose that we had an obtuse triangle. That's a triangle that has an angle that's more than 90 degrees. So suppose that we had this instead. Let's say that we know this angle, theta, A and B. Again, we know the included angle between two known legs. So now, if I complete the triangle to make it a right triangle, I get this. Notice that I have a right triangle now. What I'm going to do next is figure out what this is, this angle here, because the height of the triangle is h here. So if we do this instead and we find theta bar, then I can say, well, theta bar is exactly 180 degrees minus theta. Theta bar is 180 minus theta. Now, for the sine function, it doesn't actually matter. Sine of theta bar is going to be the same as sine of 180 minus theta. You could look at that on your unit circle whenever you want. It's the top half of the unit circle is positive. Sine of theta bar is the same as sine of theta in this case. So, again, sine of theta bar is going to equal opposite over hypotenuse. A is our hypotenuse, h is our opposite side. So we get h divided by a. Again, if we solve for h, we get h is equal to a sine theta bar. Now, as I already noted, sine of theta bar is identical to sine of theta when theta bar is equal to 180 minus theta. So h will equal a sine theta. And you'll have to trust me on this unless you want to look at the unit circle. So if we look at here, an angle theta, let's say that our angle theta was more than 90 degrees. So we have an angle like this. This point, this height, would be our sine of theta. That's what it would be. Now, if we look at instead theta bar, which would be 180 minus theta, then we're looking at theta bar being this angle here. This is theta bar. Notice that they're at the same height, the y value. The y value of these two is identical. That means then that sine of theta bar is the same as sine of theta when theta bar is equal to 180 minus theta. That's where I got this. So since we know the height of this triangle, we can use again this formula, 1/2 base times height, to get the area of this triangle. We'd get then a is equal to 1/2 a times b times sine theta when the angle is included. What we've shown here is that for an acute triangle and for an obtuse triangle, we have that the area is 1/2 ab sine theta. Go ahead and formalize this. Area of a triangle. The area of the triangle with side lengths a and b with included angle theta is a is equal to 1/2 a times b times sine theta. And we just went over this in the last slide and showed how to prove this. Now, I will note, you do need the included angle theta. You can't use an angle that's not included. But let's go ahead and do an example just to show you how this works. Find the area of the triangle. Suppose this is our triangle. 4, 12, 150 degrees. You should go ahead and try this one on your own because this is basically just plug and chug. What I'm going to do is I'm going to call this side A and this side B, and we can see that the angle between them is 150 degrees. That means the included angle is 150 degrees, which is what we need. So we have side length A, we have side length B, and we have the included angle. So we just use this formula. A is 4, B is 12, and theta is 150. So we get A is equal to 1/2 times 4, 12, times sine of 150. This is equal to 4 times 12 is 48, divided by 2, 4, and then sine of 150 is 1/2. We have 24 divided by 2 is equal to 12. So the area of this triangle is exactly 12 units. Go ahead and try one on the accompanying worksheet. Find the area of the triangle. You're just going to use the same formula. All right, that's going to be it for today. I will see you all in the next lecture.